Welcome everybody. Today my presentation is on Vibroacoustic, a rapid diagnostic approach for on-load tap changer. During this presentation, we will show how the Vibroacoustic method is used as a fast diagnostic tool to easily detect mechanical problems in the tap changers online or offline before they create an outage. So over the next 5 sections, we will uncover the full potential of this diagnostic tool and demonstrate the significant advantage it can provide. 40 to 50% of failures on transformers come from tap changers and are of mechanical origin. 4 studies done by Hydro-Quebec, ESCON South Africa, Canadian Electricity Association, and Australia for 10 years on 3 continents showed the same results. Segre and IEEE confirmed these results. Table shows a brief comparison between the 5 existing methods of presently available in the industry for OLTC maintenance. This table is from Segre, and Vibroacoustic is also recommended by IEEE. For example, you can see that overheating and cocking is marked low for Vibroacoustic, but is marked excellent for timing, transition, and arcing. As you can see, the Vibroacoustic methods offer the widest detection spectrum of detection. So we can detect brake problems, selector, lack of lubrication, contact wear, and many other problems related to OLTC. Sorry, I have how an OLTC works. Fact, we need to move from tap 1 to tap 2. How to do it? On left picture, simple changing of taps during energized status is unacceptable due to momentary loss of system loads during the switching operation. On right picture, sorry, Randy, I have some on the right picture, the make before break contact concept shown in figure 4 is therefore the basic design for all OLTCs. The transition impedance of in the form of a resistance, resistor or connector and sorry, Randy, I have a problem with my screen here.
Okay, that's all right.
Yeah, I need to.
Yeah, take a minute to sort your screen out.
I need this because I don't know. I got some technical problems and I don't know how to solve it because it's some. Okay. Thank you. So sorry. So just I'm in slide 6. So yes, in fact, we need to move from tap 1 to tap 2, and I told you how to do it. On left picture, the sample changing of taps during energized status is unacceptable due to momentary loss of system load during the switching operation. On the right picture, the make before break contact concept shown in figure 4 is therefore the basic design for all OLTCs, and the transition impedance in the form of a resistor or reactor consists of one or more adjacent units that bridge adjacent taps, and the idea is to transfer the load from one tap to the other without interruption on minimum change in the current load. With an OLTC comprising a diverter switch and a tap selector, the tap operation takes place in 2 steps. The next step is first pre-selected by the tap selector at no load, you can see the vibroacoustic recording of the two impacts produced by the tap selector on the left. And on the top, you can see the zoom of the two impacts of the selector. The diverter switch then transfers the load current from the tap in operation to the pre-selected tap, and you can see the impact produced by the diverter and the zoom of the impacts on the top left. Here you can see the details of steps of a diverter switch transition from tap 3 to tap 4 in a resistor OLTC type. The changeover must be made quickly in 40 to 60 milliseconds to avoid overheating the resistance for OLTC resistor type. So we are able to listen to all the impacts during the step up or step down operation. And here we can see a zoom of the impact of the diverter. So the motor allows the tap changer to move from a position to another. In recording analyzing the EC or DC current of this motor during the step up or step down operation, we're able to know if the mechanisms are forcing or not. The motor current allows also to start and stop the recording. The motor operates between 2 and 12 seconds. So, methodology for the vibroacoustic. Each operation of any OLTC produces a specific vibroacoustic wave pattern or signature, or we call this a fingerprint also. With a vibroacoustic sensor, which is an accelerometer, we can record this signal exactly the same way a stethoscope picks up a person's heartbeat. And a stable OLTC always shows consistent signatures, and any degradation of the OLTC induces change in the signature. A total of 14 benefits have been identified. I present here for the benefits of the electric utilities. And here I present the most important ones. It's applicable to any kind of tap changer, applicable online or offline, and now more the maintenance is they try to push the online maintenance instead of the offline, just because the needs for electricity is so huge. And the third point is the quick, easy, and intuitive test like a stethoscope, better understanding of how the tap changer works, excellent in terms of timing and mechanical adjustment. And also it's an excellent tool to help the user to decide which OLTCs are due for a maintenance operation. In order to apply the vibroacoustic method, the user will need the following equipment: a current transducer, EC or DC, the tap changer vibration analyzer tap 4 plus, a computer with a software OpenZen tap, at least one accelerometer per phase with the related mounting base. Here you have an example of connections for a tap 4 plus, which is a portable instrument. So you can see on the top left, like the tap glue first, the tap base, and the accelerometer, and the connections to the front panel. Here, the EC or DC current clamp, and then this is the minimum that we use, and also the tap 4 plus with the computer connected through the USB. We have for the next here, we have also the other one, the OTMX, which is a standalone monitoring instrument. So it's exactly the same installation, except it's permanent, or it could be used also for a period of 3 months, like a temporary installation. So here, just to fix the idea, we have here is a YouTube video to show you how and where to install the accelerometer. So first step. So I hope everything is going well. First step, we need to identify. Oh my God. Yeah. Can you see the video, Randy?
Yes. Well, it's more like a moving slide. It's okay. We can.
Well, okay. First step, we need to identify the tap changer and the motor drive mechanism. This is the first step. Here you can see the tap changer on the left. And here I told you about the glue. I told you about the mounting base. Say, first we have to identify where to install the accelerometer. So here we're going to install it on the bottom of the tap changer. And here it's the control cabinet where we will install our EC or DC clamp. So here, the person here is putting the glue on the mounting base. And the accelerometer should be installed at the closest possible location to the transition mechanism. So the aluminum base is glued at the best location for this type of OLTC, and the accelerometer is screwed into that base. In fact, this cable is connected after to a BNC cable if you need like 25 feet, 50 feet, or 100 feet from for the recording system to the tap changer. So the accelerometer is installed. So here the current clamp installation on the motor drive. So you see on the top the EC, the current clamp, and the guy is starting just the tap, step up or step down, and the system records is triggered on the motor drive. And here we can see a test sequence. So here the user starts the step up or step down, and immediately the recording of the current on the bottom and the accelerometer on the top. Green means that the operator can do a step up or a step down. The recorded data are transferred to the computer, and they are immediately visualized. Here you have a two sequence. You have a two step down in the same. Here it's the step up or step down here. Okay, I think, okay. So the sampling time is an important parameter to consider. All our recording are done with a sampling time of 10 microseconds, which is an excellent choice for vibroacoustic signals. In addition, we have a large database of recording that facilitate the OLTC's comparison. So here you can see what is a good and what is a bad vibroacoustic recording signal. On the top here, you can see in green 10 microsecond sampling time that we recommend strongly to record a vibroacoustic signal. you have here, just in comparison, exactly the same vibration of a ball bouncing on a plate, recorded at 100 microseconds. So this kind of sampling time is okay for timing motion, but not for vibration. And here, just to show you what it means, the sampling time, it's 500 microseconds, which gives a totally broken signal. So in the next slide, you will see the a zoom of the impact, and you can see that the 10 microseconds record is signal is smooth and continuous, and the others are broken. So in fact, if you want to analyze your signal with a 100 or on 500, you have nothing. It's just noise. So here a comparison of 3 accelerometers attachment methods, and with glue, magnet, and beeswax. And here we have done some comparison. I have received a lot of questions regarding the attachment methods and why we use the glue instead of the magnet, which is easier to use. And to answer this question, we have done recently the comparison of the 3 accelerometers attachment methods. Here you can see the beeswax on the top, the magnet in the middle, and the glue on the bottom. And here, so this graph shows a zoom of the impact section of the recording. On the left, you can see the raw data here. And on the right, you calculated the envelopes for the same data. And in next slides, we'll present what is an envelope. And next slide will show the detailed analysis. So here the envelopes are zoomed. And these graphs, so we have superposed the 3 signals, and this graph shows the result of the 3 attachment methods superposed, and we see clearly that glue and beeswax are identical, but for the magnet amplitude of the signal is drastically reduced, and an additional impact is introduced. Even if magnet is convenient, it has 2 major problems: the reduced bandwidth of the accelerometer signal, and the fact that we lose the location of the accelerometer for the future test, which would negatively impact the analysis of trends. So when you analyze so it's really clear that beeswax and glue are the best, and we do not recommend the magnet. So here you have some example of accelerometer installation. So in fact, the idea is just to be as closest as possible to the diverter. So a good habit is to know the architecture of the OLTC, and then try to figure where to install our accelerometer. Here you have some examples of current clamp installation. Here I can notice one thing. You have some, in some countries, the OLTCs are, the motor drive is with DC, and the others are AC. Here in Canada and North America in general, it's EC. And like in Europe, specifically in France, Morocco, North Africa, they are in DC. So for online test, presence of high voltage, we record operation of 1 or 2 taps, step up and then step down of 1 or 2 taps. Tests are performed to minimize the impact on the consumers. For offline test, we record all taps to get a reference. We recommend to get a reference of each transformer with OLTC of your park of transformers. With these recordings, you could establish your predictive action maintenance plan for all your transformers with OLTCs. On the left, you can see the raw data with the envelope superposed. The Hydro-Quebec envelopes have been patented by Hydro-Quebec in 2001. On the right graph, you can see the envelope for the current and the high frequency and low frequency envelopes. So why envelopes? Simplify the signal, get the shape of the signal. We focus on variable impacts only, easy to analyze, easy to compare, and help to detect wear contacts. Every tap changer has a specific sequence of operation that can be identified in the envelopes. Depending on the model of OLTC, different signatures can be obtained, which are characterized by specific operation length, number of impact, amplitude of the impacts, shape of the current, and so on. And the sequence of operation associated with an OLTC is described in the operation guide provided by the OLTC manufacturer. Most of the times, this guide describes the operation of every single mechanical element acting during the switching operation, such as the diverter, the selector, the auxiliary contact, the main contact, and so on. With this information, the relation between impacts and mechanical parts can be easily identified on the footprint as shown in this picture. Despite its apparent complexity of interpretation, the vibroacoustic method represents a straightforward verification of predetermined repetitive steps. Here you have some example of timing chart given by the manufacturer for a diverter switch, and this chart explains how and when the transition occurs during the switching of the diverter. So I recognize that sometimes it takes time to understand each impact with the transition contact. But we have developed well, I will present in the next slide. You will understand what I mean. First, mathematical processing is done by calculating the envelope for the current drive and the vibroacoustic signal. So everything starts with the raw data, and the diagnosis can be made in quickly for an online test and 1 hour for an offline test, because in the offline test, we go through all the taps up and down. So as soon as we get the raw data, on site, we calculate immediately the envelopes thanks to the software. We get an Excel report, which target specifically the taps with some problems. So it's in dark. And then from here, so immediately we can detect problems, as I will show you in the next slides. And after, when we get these two reports, the envelopes and the Excel reports, we can do an off-site deep analysis. So thanks to the Excel reports, contact wear, envelopes, diagnostic cards, and also we have a database where we can compare with the reference signatures. So vibroacoustic diagnostic findings, detected problems. So next slide, we show examples of detected problems. So this is a typical case where the high frequency and low frequency compression give good information on the degree of wear of contacts. Before the intervention, more than 60% difference between the high and low frequency envelopes. With exactly the same, after repair, after the intervention, less than 20% difference between the high and low frequency envelopes. And here an example of poor lubrication for the motor drive current. In fact, the torque is forcing. So here, in general, this plateau is totally flat, and here we can see that the current is increasing, and this is not normal. Other examples of abnormal inrush current. So here the inrush current is delayed, which is not normal, and this delay has a consequence that the breaker opens. So it was like a totally new installation, but with a bad adjustment. And here also it's forcing current on the bottom here. Here is an example of motor drive current analysis throughout the years. We have the recording done in 2014, 2016, And you can see here that the motor current was not normal. So we notice easily, this is the kind of problems that are easy to detect. You don't need to do some trending or some deep analysis for these kind of problems. So this test shows an example of asynchronism of the diverter switching operation. In normal condition, the switching operation should occur before the current stops flowing in the motor. In the case illustrated on the left, the switching operation signal is delayed by 120 milliseconds after the end of the current envelope. As it can be easily observed, this kind of issue doesn't require the use of reference signature, and the asynchronous can be detected immediately. The intervention in this case consisted in coupling the drive motor and adjusting it so that the switching operation could occur before the motor current drop. And the figure on the right represents the normal condition of the mechanism after the repair. In this picture, an example of arcing contact is presented. Two tests have been performed on the tap number 10 of the same OLTC. One test has been performed offline, the red curve, and the other one online, the black curve. By comparing the two signatures, a big difference in the maximum amplitude can be easily observed. In fact, the maximum amplitude of the offline test is 8G, while the one of the online test is 35G. The image on the right shows the superposition of the two signatures, through which it's possible to observe the presence of an extra peak in the online test, and this extra peak represents the arcing contact phenomenon. So the last part will show how the combination of vibroacoustic, motor current, and dynamic resistance measurement signals increase our analytical capabilities. By combining vibroacoustic, DRM, and motor current signals, we can easily identify components such as the tap changer diverter, transition resistor, and moving contacts, analyze the sequence timing of a complete tap change or multiple sequential tap changes, verify the sequence timing of a specific component. Here, example of setup with tap 4 plus and tap DRM combined. So in fact, you have the instrument, the accessory, which provide the power source, and the measuring for the DRM, because with this, after we can get the DRM, so dynamic resistance. Here you have the EC current clamp, the accelerometer, and of course, the transfer connections offline. DRM is done offline. It's not like if when we are online, of course, we cannot put the DRM. So starting from the top, this graphic shows the dynamic resistance curve, the accelerometer readings, and the motor current signal. Here you can see the correlation between the dynamic resistance and the vibration signal during the diverter switching. As it can be observed, the accelerometer signature is characterized by 4 main peaks, the 2 first corresponding to a specific value of current. With the support of the video, these first 2 peaks have been identified as follow: first impact of the first auxiliary contact entering the new tap position, second impact of the main contact entering the new tap position, and the 2 final impacts are not related to the main contact of the switching taps. So in fact, it helps you, like when we are online, we don't have access to the DRM, but thanks to the knowledge, to the recording of an offline test, we can learn the vibroacoustic signal, so the accelerometer signal, and then after, when we are online, we can easily understand what all these 4 peaks means. So here is another example of Vibro DRM motor testing. New Brunswick Power was able to do a complex timing adjustment of 3 diverters on phase A, B, and C with vibroacoustic combined with DRM and motor current. This maintenance was performed on Caracat T1 transformer, and this transformer is equipped with a Renhausen type M3 delta tap changer. The timing between the motor drives and diverter assemblies is adjusted using the shaft connections between them. In this up operation, tap 3 to tap 4, we are seeing that A phase is operating earlier than B and C. So I think it's clear in the graph. This arrow is less, the size of this arrow is less than the 2 other B and C. So here, after maintenance results now indicate the timing between all 3 phases is now better adjusted, and the selector and diverters operations are now synchronized. So example of a good after repair. But in the down operation, we are not only seeing that A phase is operating slightly later than the other 2 phases. In fact, A phase is operating after the motor current is interrupted. And the timing of this diverter is at the limit where it could possibly not operate during a down operation. So this would result in a phase being on a different tap than the other 2 phases. So here we can see clearly that the motor current has stopped, and the diverter switch is operating after. So this is clearly dangerous. And big improvement can be seen on the down operation, where A phase is operating well within the runtime of the motor now. And this aligns with what was seen for B and C phase. So here we can see that the diverter switch now has been adjusted correctly, thanks to the vibroacoustic and with the DRM also.